Morning. I'm Nikhil Puri from Cambridge Systematics. I've been working in the field of travel demand forecasting for about 15 years now. And for those of you who are not familiar with travel demand forecasting, it's essentially a science/art of predicting what future travel behavior would be. And we do that using sophisticated models and a lot of data. So this presentation is essentially to do with using robust transit information available out there, published by agencies in travel demand models. One of the things I've noticed over the years, and this is not just peculiar to this region, is that travel demand forecasting models don't have a lot of good data, especially related to time, feeding into them. And given how much data is available out there, we as an industry need to recognize that using these data that's freely available especially is critical to some of these models understanding and representing things like travel times. So just to give you an outline of what I'm going to be talking about, we'll talk a little bit about the motivation behind the work that we're doing. I'll give you a sense of what the GTFS feeds are all about, an overview there. Talk a little bit about the New York best practice model, which is what we're working on right now and updating. And we'll be using the GTFS feeds, that's the transit schedules essentially, in this model to better represent schedules and so on. And then the actual conflation process of conflating GTFS feeds with the model networks so that we have a better integration between the actual data and the models themselves. So the best practice model, the New York best practice model, covers about 28 counties in the region. And so we're trying to get GTFS feeds for as large a region as possible. And at this point, we've got about a 70% coverage in terms of feeds available and feeds that are usable for the region. What are we trying to do here? We're trying to get a better sense of travel times and transfers and access and egress times that feed into the model. We are trying to reduce the amount of manual work in terms of manual coding of networks. And I think one of the most important aspects is to integrate the highway side and the transit side of the modeling process. And why that's so critical is because you have access and egress to a large extent happening on your highway networks, which then feeds into a transit system. People driving from their homes to a transit station, for example. The transfer links and the transfer information within stations in a subway system or a train station. Those are elements that are crucial to any model, whether it's understanding existing travel patterns or predicting out into the future. And so it's critical that those elements have robust data feeding into them, and with the availability of a lot of these data, it's encouraging that a lot of the industry now is beginning to think about using some of these data and have actually started using them. So the focus here is conflation of the GTFS feeds, and I'll get into what GTFS is in a little bit, with the New York best practice model network. As far as we understand, there are not a whole lot of applications at this scale, and then again, it's extremely exciting. So GTFS is essentially the General Transit Feed Specification, which used to be called Google Transit Feed Specification. They're essentially electronic versions of schedules that are published by agencies and are now a de facto standard as far as schedules are concerned, transit schedules are concerned, and are used in several applications, especially to do with routing and planning. So just to give you an example, when you go into Google, for example, and you want to plan a transit trip, you get information about your walk access to a station, you get information about in-vehicle times on your transit vehicle, you get information about your egress, the egress component, and so on. And that's the kind of information we'd like to use and feed into these models. To give you an idea of what the structure looks like, you have information, this is again GTFS structure. You've got information on the agency that publishes the data. You've got information on trips, that's essentially going from point A to point B, the number of routes, the days of operation. You've got information on stops and travel times between stops, and fares. So it's essentially all the information that you need to feed into a travel demand model. Why is it not being used as extensively as it should be? Well, it's gaining in popularity now. But one of the main challenges is conflation, is to essentially associate the information in some of these really large data sets with your networks, and that's essentially what we're working on. Is it going to be seamless? No, probably not. I mean, you have algorithms that we're working with now to conflate these feeds with networks, and you're going to run into issues. But it's a lot better and a lot more efficient than coding some of these networks manually, and it's an evolving process where we're learning more about how to improve things. Now, there's not a whole lot of guidance out there. We are in the process of working on examples like this. We're working on things across the country using some of these big data sets, so we're learning a lot from it. So while we're doing all this, again, this particular effort is focused on using the transit feeds in the New York best practice model. And as I mentioned, if you think about the different elements of a transit trip, you've got access, you've got in-vehicle travel times, you've got transfers within a system, you've got egress times, and all this information, as I mentioned, is available. And the good thing is it's freely available and published by agencies, so you can be sure of the quality of a lot of these data that are available. So just to give you kind of an idea of what it takes to update a model or a model network, we initially identified GTFS routes that can be used. So as I mentioned earlier on, we've identified about 70% of routes that can be used within the New York best practice model and can feed into it. We've also, in order to conflate some of these feeds, it's a lot of data. We've written an algorithm. CS has developed an algorithm to actually do that. My colleague Michalis Sinterakis, who's going to be presenting next, has actually developed that algorithm himself. And we've also tested other off-shelf applications which do work but are in their infancy and so have issues. And we experience some of those as well. But again, it's becoming more common. One of the main issues here that one faces when conflating these feeds with highway networks is that you don't have enough highway network detail, which is lacking, and so one has to go in there and essentially add the highway network detail, and so that's an iterative process. But the idea behind conflating it essentially from a travel demand modeling perspective is to develop what we call skims in the industry, which is an idea of the cost between point A and point B, and this is in terms of travel time in this particular case. So you'd want every element of travel, every element of your travel trip, which is what skims gives you, and that's the final objective of what we're trying to do here. We're trying to derive skims which then feed into all the other aspects of your travel demand forecasting model. Obviously, it's not going to be seamless. It's a semi-automated process because you run your conflation algorithm, you get a reasonably good match. In this case, I think we've got up to an 80% match between the GTFS feeds and your highway network, but the rest of it is going to be manual. And of course, there's a lot of good information out there that's already fed into the development of an earlier version of the model, of the existing version of the model. So we're going to be using a lot of that information. We're going to be reaching out to agencies. There are a lot of agencies we're working with already who are giving us good insight in terms of what's there in the model, what should be used, and things that can be improved. So just to give you an idea, for those of you who haven't dealt too much with network models, they're not perfect. They are essentially line representation, line and node representations of a roadway network. And what you see here is that the red lines are your GTFS routes, and your gray lines are the highway network. And in this particular case, on the northern side of the figure, you have one single line representing a roadway. So again, it's not perfect, but you have imperfections on the GTFS data as well. I mean, you've got errors in coding, you've got alignment errors, and so on. So there's a lot of manual intervention that's going to be needed in this kind of an update. So again, what is network conflation? It's the association of one network with another. It's an association of a node layer with another. You're essentially trying to get information from one layer into another. In this case, it's from the GTFS feeds to your travel demand model. It has been a serious problem in terms of using big data in any transportation planning application. That's something that we're grappling with right now. But hopefully, projects like this will help alleviate some of the issues that we faced. So the algorithms that have been tested on this particular effort have ranged from just trying to snap nodes. So you have your GTFS feeds essentially have transit stops for representing each route. Now those stops are then snapped to the highway network node. So that's one process that was tried. It didn't work very well. We ran into some issues there in terms of not finding relevant routes. We've tried some heuristic methods in terms of just defining rules and found that those have spun out of control pretty quickly. And now we essentially use a process by which we are optimizing the area between the two routes, and so your conflation from that standpoint it's worked pretty well. We haven't run into the same kind of issues that we have in the past, and if we have any specific questions, we can direct them to Michalis. But here, just to give you an idea, on the left we have the entire route, and on the right what you see is a particular conflated route that is different from, it doesn't align specifically with the highway route. And what's happening there is that because there isn't enough detail in your underlying highway network, the algorithm now finds a parallel path. And so from that standpoint, the algorithm works pretty well. One of the main issues is not having enough highway detail, and so it's a question of going in there and adding the detail on. But even when you don't have enough detail, the algorithm finds parallel paths. This obviously takes a lot longer to do because you're finding paths that are not realistic in many cases. But that's where really robust QA/QC is required. Just to give you a quick idea, we've developed the algorithm in Python, and it has worked pretty well for this particular application because it's essentially a one-time application rather than having to repeat the runs over and over again, and have achieved about an 80% accuracy in terms of the match. We've also been able to test the conflation in terms of bringing it into the travel demand model and for a pilot region, developing routes and skims, as I call them, which is essentially travel times from one origin to a destination within a particular region. So that's worked as well. As far as next steps are concerned, we'll be developing skims for the region. We'll be obviously testing and validating, and hopefully done by May of 2017. So with that, I'll take any questions. Yes.
So these schedules, how long are they valid? I mean, aren't you predicting out 20 years and you're trying to assume that the bus line that currently is in Manhattan is going to be the same on 20 years?
That's a great question. I mean, it's very similar to what happens now, which is we code in information that exists according to schedules, paper schedules right now. The only difference here is that these are electronic. And so every time you need to update your information, it's freely available. And from what I understand, a lot of these schedules are updated on a yearly basis. So you have the ability to update as and when they do. However, when you go into the future, you got to make certain assumptions. For example, your fares are kept constant in a lot of travel demand models. Your tolls are kept constant. So you need to make a decision as to whether you need to revise your service in any way or not. That's a conversation that you need to have with some of the agencies involved. Yes, sir.
Can you go into a little bit on the infrastructure of the hardware and software you use for this?
Michali, do you want to talk a little? You probably should take this.
Okay, so as Nikhil mentioned, so the algorithm is developed in Python using some open source libraries, GIS open source libraries, and we're also using Transcat for the travel demand model.
You mentioned large data sets. What database are you using for that?
So we're using the GTFS. So GTFS is a collection of CSV files, so one may not, so you can put GTFS in a database, but you don't actually need a database to query GTFS. So the CSV files are loaded internally in some data frames, which is also in R, the same terminology are used.
So just to give you an idea, those files can be opened on a regular laptop. I mean, these are essentially text files, several text files that have data about routes and stops and travel times and fares and so on.
Did you customize Oracle or DB2 to do this?
No. So the reason for a database, one of the primary reasons is like to have some records in and then update them constantly. So you have a customer database and you have new customers, so customer piping. So GTFS, I would say it's static. So it has the information there that for, say, 6 months do not change. So whatever we tried to do did not change the GTFS database, so we didn't have to update it or change it in any way. So we just want to take this information and then import it and use it in modeling. So this is why GTFS functionality like querying or updating or changing records did not pertain to this application.
I'm sorry, I just want to get it straight. The native mode of the GTFS database is what? That's what I wanted to get. What's the native mode of this?
Native mode is transportation mode, or
No, I'm talking about the code that holds the data.
so it's just a text files. Text
Text-
files,
it's
CSV
all
text
text.
files, you can open them yourself.
I'm sorry.
Maybe he can give a little bit more explanation during your presentation, right? It's somehow related to your presentation. And then at the end, if there's any time left, we could ask questions to all four presenters. But right now, let's welcome the second presenter, Michaelis Sintarakis, also from Cambridge Systematics. And his presentation title is Analyzing Driving Behavior at the Micro Level Using Instrumented Vehicle Data.
Okay. All right. So just a very quick comment about the last question. So GTFS has become the de facto standard, and one of the major factors for standard adoption was how simple it is. So yes, it was like a more, I would say, better structure. It would have been easier, more consistent. However, having it as a CSV files that you can load it on in Excel and see what's there has contributed significantly. There have been alternative standards, but the last 10 years, GTFS has been everywhere. So in my presentation, I want to talk about analyzing driver behavior at the micro level. And when we talk about micro level, we talk about sub-second level, in which we measure the distances between a vehicle and the other vehicles, and we see how the driver responds to, say, stimulus for the external environment, the distances from the other vehicles, how if another vehicle brakes, how the driver changes lanes. So you may be surprised that this type of data, someone may call it naturalistic driving data, although in our study it cannot be classified as naturalistic, do not exist in public. There are not that many data sources. Okay, so how do I make the slides? Right. Sorry about that. And there has been a lot of talk about connected vehicles and how they're going to change the traffic stream and how more efficient traffic flow will be. Now, in order to understand the impact of connected vehicles and their interaction with other vehicles, we need to better understand how drivers respond to events. So as I said previously, there are not that many databases out there. They have been, but they are close to the institutions that have been collecting the data. So in this study, we'll collect the data. We collected the data at University of California. We worked with the University of California, Berkeley, to collect the data, and we're publishing all the data. And this is an overview of my presentation. So in this presentation, I'll be mostly talking about data. I'm going to show you some of the radar data and GPS data. And at the end, I'll talk about measures of driver behavior at the microscopic or trajectory level. So we use a high-precision GPS called real-time kinematic GPS combined with the inertial measurement unit. We use multi-mode radars at the front and the rear of the vehicle. The vehicle also has video cameras, and then we also get data from onboard sensors. I'll talk about the variables in the collected data. I'll give you some examples of all this. So let's take a look at the vehicle itself. So it has two wide-angle radars, one at the front, one at the rear. It's about 90 degrees, but in the data you actually see that you can actually get a 100-degree field of view. It has a GPS that you probably may not have heard before. It's called real-time kinematic. It can achieve centimeter level accuracy. It's like an inch level accuracy. And this happens, of course, only when it sees enough satellites, 4, 5, or 6 satellites. When there are trees or other obstacles that prohibit the GPS device to access them, then the accuracy decreases substantially. That's why we have inertial measurement units. So it has a gyroscope and accelerometers. So when the GPS cannot find the satellites, the inertial measurement unit calculates the differential positions. I have a couple of video cameras, and we're getting other data from the vehicle. So this is the data collection site. So data has been collected in the same site previously. This is in San Francisco, and this is in Berkeley, California. So the vehicle goes on I-80 north for about 2 miles, and then makes a right turn on University Avenue, and then goes down on San Pablo Avenue, and then goes to a parking lot. There it stops for 5 minutes. The drivers take some logs and some record what happened during their trip. And we had also one accident there. Someone hit the vehicle. The driver was while they were driving it. So this is about the route's about 7 miles. You can also see a satellite image from the route. And the basic idea was that we collect as much data we want, as much data we can from incidents and weather, and see how driver behavior change. We wanted also to collect data about arterial versus freeways, because most of the data that exists now, at least in our field transportation, is about freeways, and we don't have enough data for arterials. And we wanted to see how driver behavior changes when the driver gets a little bit tired. So this is the driver schedule. It's 20 days, 3 drivers, 60 hours in total. The drivers did the circuit 95 times, and they did mostly in the PMP. This is the raw collected data. We have like 4 data streams. The first, each column here is the data stream. The GPS inertial measurement unit is one data stream. The radars, I forgot to say that each radar detects up to 64 objects. So in total, we can have 64 objects, vehicles, or like, it could be anything, or static objects. Then we have the canvas, we record data there, and then we have the video. So these are many data streams, and each of them has its own, I would say, system. So it's separate data streams that need to be integrated together, and whoever has done this, doing so is not that easy. So someone has to pay attention to what the time is, and has to make sure that the timestamps are very, very accurate. And I can get into that because a little bit more if you wish, like, but later at the end of the talk, because system time on the computer sometimes drifts, and we are talking about collecting data at 50 milliseconds. So we want to make sure that everything is timed very well and very consistently. So we're using we use GPS time. So this is offline calculation that we've done in the data. So the GPS gave us, during the GPS operation, you get a certain amount of accuracy. To improve this accuracy, you need to apply differential corrections. You can do this online or offline. So our job was doing offline. And then after we apply the differential corrections, then we could achieve the centimeter level accuracy. And of course, a lot of data at a very raw bit level that we had to work with. And then we had really a number of post, I would say, GIS operations to improve data. So one of them is to apply interpolation, because the data do not actually come every 50 milliseconds. So they can come a little bit early, a little bit later, and this is how the data are being collected and being. So the system is this how they collect the data. So and our job was, in order to have a consistent data set, just to report everything every 50 milliseconds, and for this to interpolate the data. So this is the same variables that you see before, just after interpolation. This is a slide about the driver logs. They recorded weather, sunny or cloudy, traffic conditions. There are crashes there very frequently. So I'm just going to show you some tracks from the GPS. So this is 5 runs from the GPS. So the red line sees what the GPS unit provided us after post-processing. And this is the centimeter level accuracy GPS unit. And you can see the lane changes, how accurately they're being represented. This is I-80 North. On the right is University Avenue. And then there's Pablo Avenue. In San Pablo, you see the trees over there. So actually the GPS unit lost the connection there, and was the IMU unit that provided the positions. And this is the end of the right-hand side. There's the end of the route. I'll show you some radar data. So the GPS data were very smooth, very accurate. The radar data have a lot more, I would say, problems. So radar data have about 1 meter accuracy, 3 feet accuracy. But you can see that, and this is one pass of the vehicle, and this is the forward radar. And you can see how wobbly the trajectories are. And it's actually, some of the trajectories have problems. Like the one at the bottom, you see like as if there was a vehicle that was crossing the street. Like so someone needs to process the data and clean all these things. And this is actually what makes it hard to have a collision warning system or other such devices operate properly. And it has, although now they're very, very good, but it took them quite a bit to achieve the level of accuracy, because radars give a lot of false positives, and this we see now firsthand what such data look like. This is a schematic of what can be done with the data we have, and you see here that someone can obtain positions from the lead vehicles, and so because the radars have a wide angle, you don't just get information from the same lane, but also from the adjacent lanes. Okay, so this is the process data, and on the left-hand side you see the GPS data. You see how the data, which is every 10 seconds here, how they follow the center lines, and how when a vehicle changes lanes, you see how the dots are, and then how smooth it is, and how realistic it looks like. So Its vehicle track is being color-coded by the lane it belongs to. That's why you see the different colors. On the right-hand side, you see what the data looks like for a single pass. And so there's a lot more dispersion because the radars capture not only the other vehicles, but also the shoulder and trees or whatever you are around. You have a lot more noise in the data. And our job is to blend them a little bit and then to publish the data set. This is a radar, actually the raw radar data. So on the top chart, radar gives you the range, how far the other object is. And on the second chart, you see the radar angle. So the radar gives you the range, how far the other object is, and the angle from, and you see how a little bit wobbly it goes up and down, so it's not that stable, the angle. And as a result, this is why you see the radar positions of the other vehicle going a little bit left and right. They have a lot more checkers. This is some of the charts that we have done so far. On the left-hand side, you see both charts are acceleration versus speed using the collected data. And the first, the left-hand side is on freeway segment, and the others are on arterials. On the x-axis, there's speed, miles per hour. On the y-axis, it's acceleration. So this shows you the bandwidths of speeds, the bandwidth of acceleration at different speeds. It's shown as percentiles. So for example, at 70 miles per hour, you see that the 99 percentile of acceleration is about 4 feet per second squared. At lower speeds on the freeways, you see at about 10 miles per hour, you see the 19% of acceleration being a little bit higher, 6 feet per second squared. On the right-hand side, you see the arterial plot. So you see that drivers accelerate and decelerate much more aggressively on arterials, and that's because of the signal. Reaching up to 10 feet per second squared. So this is some of the things that someone can do with good data, and we have not integrated yet the radar data in the data set that shows positions. Okay, so lessons learned. So the integrated GPS with the National Measurement Unit is very easy to work with, but we have a lot of problems to configure the data, the radar data, and a lot of problems to get good radar data. One of the biggest problems is that the data came asynchronously. So, and then we had to build the infrastructure and the code just to obtain it and write it very quickly to the disk without much lag. And just very quickly talk a little bit about the microscopic measures of travel behavior or driver behavior that we plan to use. One is time to collision. So using the radars, you know how distant the distance to the leading vehicle, so you can calculate the time that the two vehicles will collide if they continue on the same trajectories. And then there's other measures about acceleration, noise, acceleration jerk, which is actually the difference in acceleration between two time steps. And it's been used actually very as a design measure in many applications, including elevators, because this is a measure that describes how comfortable the ride is. For lane changing, there's a travel time measures that travel time to collision measures that can be applied that show how I would say efficient and how dangerous is a lane changing maneuver that the vehicle had done. So this was my last slide. Yeah, it stopped working. I mean, I had like one slide more like about next steps. That's it, okay. Clean the data, expand the macroscopic measures presented, and then publish the data. So these are the next steps that we're planning to do in the next 6 months in 2017. That was about it.
Question. So my question is whether your presentation or your research is related to the previous one or how, since you are from the same company, right? Yeah. If not, then have you ever considered the urban canyon effect in a city like New York, because the data is collected from somewhere almost without buildings, or very low buildings. But urban canyon, in fact, is really serious in New York City, and so that would definitely affect the accuracy of the data.
That's true. That's true. So the GPS and IMU unit we use actually we configured it to work well in Berkeley, California, where we have like a few bridges and then we didn't have that big canyon effects as here in New York. More expensive units will provide you better accuracy and really good accuracy here in New York City. So there are inertial measurement units that are very, very expensive, much more expensive than GPS units, that will provide you the position of a vehicle without any GPS here. And these units are being used here in New York.
The study was done in April and May, so there's no inclement weather whatsoever in Berkeley at that time of year. Why was it done then as opposed to, driving in rain, driving in other types of conditions? The only type of condition I can imagine is, depending on the time of day, it's the sun shining in the side of the face of the driver.
Yeah. So there was, you're right, we had a little bit of drizzle, and this is one in the driver logs that I showed. We have rain. We had rain Monday, in which we have test data, okay? But it was a bad year in California, and we had 20 days that we can collect data, and there are other parameters. And, when the project is running, and that's why I say, okay, this is the time I have. I'm going to collect data, and whatever I get, great.
All right, so if there's any more time at the end, we'll open the session for questions.